Welcome back to Mechanical Engineering Made Simple.
It's great to be back.
Today, I want to start by asking everyone listening to do something for me. Picture the engine in your car, or maybe a massive gas turbine on a jet wing.
Okay.
When we think about what's happening inside, we usually have this very sanitized high school chemistry version of it.
The textbook burn, as we like to call it.
Definitely. It's this neat little equation. You have fuel, you add air, you get a spark, and poof, you get heat, carbon dioxide, and water. It's, linear, clean.
And it implies that if you just get that mixture right, you get 100% energy release and totally harmless exhaust.
Which is a lovely fiction.
It really is.
Yeah.
If combustion were that simple, my job and the jobs of thousands of combustion engineers, well, we just wouldn't exist.
Because the reality is less of a polite handshake and more of a riot.
A battlefield. That's the word for it. If you could zoom into the molecular level inside that cylinder, you're not seeing a one-way street where reactants just become products. No, you're seeing a chaotic state of what we call dynamic equilibrium.
And that concept, dynamic equilibrium, that's really the heart of this deep dive, isn't it?
It is.
We're going to walk through the story of a combustion reaction to answer some of the most popular questions we see online, specifically, why don't engines get as hot as the math says they should?
And the big one, where do all these nasty pollutants actually come from if we're burning so-called clean fuel?
The answers you're saying boil down to two invisible forces.
Two invisible forces fighting against perfect efficiency. First, you've got dissociation, which acts like an energy thief.
Okay, the thief.
And then you've got kinetics, which is basically a cosmic speed limit.
All right, let's unpack this, starting with the thief. Dissociation. To get this, we have to look at equilibrium. Most of us remember the standard equation, right? Carbon monoxide, CO, plus oxygen, O2.
Makes carbon dioxide. CO2, stable. Done. But that's the cold view. It implies that once CO2 forms, it just stays that way. But inside an engine, we're talking about temperatures pushing, 2,500, maybe 3,000 Kelvin.
That's incredibly hot.
At those energy levels, the product molecules themselves are vibrating so violently that they start to shatter.
What, the exhaust is kind of unburning itself?
In a way, yeah. That's a good way to put it. The reaction actually becomes reversible. CO2 splits back into carbon monoxide and oxygen.
Wow.
And water vapor rips apart into hydroxyl radicals and hydrogen. That process is dissociation. And it's all dictated by the absolute grandfather of thermodynamics, Gibbs energy.
Right, Gibbs. Denoted by G. I remember the definition involves enthalpy minus the temperature times entropy.
That's the one. And the key thing to remember is that the universe is fundamentally lazy. Any chemical system will always try to move toward the state with the lowest possible Gibbs energy.
I always picture this as a ball rolling around a landscape of hills and valleys.
That's a perfect analogy. The gas mixture is the ball, and it's just looking for the deepest valley it can find.
And the composition of the gas, how much fuel versus exhaust, is the ball's position.
Exactly, and the depth of the valley is the energy state. So the mixture keeps reacting forward, then backward, shifting its composition until it finds the absolute bottom of that valley where the slope is zero.
That's the point where dG, the change in Gibbs energy, is zero. That's equilibrium.
Correct. But here's the catch that trips people up. That landscape, it isn't static. The shape of the whole valley changes depending on pressure and temperature.
So when you crank up the temperature in an engine, you're basically warping the landscape.
You're completely reshaping it. The bottom of the valley moves. So at room temperature, the bottom might be mostly CO2, but at 3,000 Kelvin, the bottom shifts to a mix of CO2, CO, and oxygen.
And what's the actual force pushing the ball around this landscape?
That's something called chemical potential. You can think of it like chemical pressure. Just like air flows from high to low pressure, chemical species flow from high chemical potential to low chemical potential. The reactants are pushing to become products, but at these high temperatures.
The products are pushing back.
Precisely. And equilibrium is just the ceasefire line, where the chemical potential of the reactants equals the chemical potential of the products.
Okay, that's the theory. But let's apply the so what factor. If I'm designing a Formula One engine, why do I care if 5 or 10% of my molecules decide to break up?
You care because it steals your power. This is why we call it the energy thief. Breaking those chemical bonds, turning CO2 back into CO and oxygen, is endothermic.
It absorbs heat.
It absorbs huge amounts of it. It sucks thermal energy right out of the explosion. So let's say you do a quick calculation on a napkin, assuming perfect combustion. Your calculator says, congratulations, you're going to hit 2950 Kelvin.
which means a massive pressure spike, which means lots of torque on the crankshaft.
Right. But then you run the actual engine, and you only measure 2800 Kelvin. You've lost 150 degrees off the top.
And that energy didn't just leak out through the cylinder walls.
No, it was consumed internally by the molecules tearing themselves apart. And that's a direct loss in peak pressure, which is a direct loss in work output.
That's a huge efficiency hit. And I see in the notes there's a metric for this, alpha, the degree of dissociation.
Yeah, alpha is just the fraction of the original molecule that's broken down. If alpha is 0, you've got a stable molecule. If alpha is 1, it's completely disintegrated.
And engineers have some levers to pull here, right? We're not completely helpless.
We have two main levers, pressure and temperature, and they work against each other.
Okay, walk us through the pressure side first.
So think about what happens when things dissociate. Let's say two molecules break down. They turn into two CO molecules plus one O2 molecule.
So you started with 2 particles and you ended up with 3.
Exactly. Dissociation increases the total number of moles in the gas. It wants to take up more space.
So applying Le Chatelier's principle, if you squeeze the system, increase the pressure, it's going to fight back.
It will try to relieve that stress by shifting toward the side with fewer molecules, which is the non-dissociated side.
So a high compression ratio in an engine actually helps suppress dissociation.
It does. High pressure kind of keeps the family together. But temperature does the complete opposite. It adds violent kinetic energy and encourages the breakup.
That is such a cruel trade-off.
Isn't it?
The Carnot cycle tells us we want high temperatures for the best theoretical efficiency. But those same high temps trigger the dissociation that steals that very efficiency.
Welcome to engineering. It's never just one variable. And there's a neat little nuance here in the data. Water is tougher than carbon dioxide.
Meaning H2O doesn't break down as easily.
Right. In your typical hydrocarbon combustion, the water molecules dissociate a lot less than the CO2 molecules at the same temperature. The water is just more stable.
Okay, so we can't just guess at this. If I'm building a simulation, I need a number. How do we calculate where this balance point actually is?
For that, we use the equilibrium constant, which we call K sub P. It's a value that tells us the exact ratio of products to reactants at a specific temperature based on their partial pressures.
And the sources mention the Van Hoff equation here.
The Van Hoff equation is just a beautiful way to show how that K sub P constant changes with temperature. It linearizes the problem. If you plot the natural log of K sub P against 1 over temperature, you get a straight line.
That sounds great for a chart, but looking at the actual math, this seems really hard to calculate by hand. You're ending up with cubic equations and systems of non-linear equations.
It was a total nightmare to do by hand.
It looks like the method is basically guess and check.
That's essentially what it is. It's an iterative loop. You see, you can't solve for the final temperature directly because the final composition depends on the temperature.
But the temperature depends on the heat release, which depends on the composition. It's a circular reference.
Exactly. So you have to guess a final temperature. Then you calculate K sub P for that temperature. Find the composition. Then you check the energy balance. Did the heat released match your guess?
And it probably didn't.
Almost never in the first try. So you adjust your guess and you do the whole loop again and again until it converges.
I'm very glad we have software like MATLAB or Python to handle that iterative part now.
We are too.
Yeah.
But you have to understand the logics to set it up. But here's the thing. Even with a perfect computer model, equilibrium has one fatal flaw.
Which is?
It assumes you have infinite time. It assumes the molecules can just hang out, bump into each other, and comfortably settle into that lowest energy state.
And inside an engine cylinder, comfortable is the last word I'd use.
Right. Let's think about the clock. If your engine is running at 6,000 RPM, that's 100 revolutions a second. The entire 4-stroke cycle happens in 10 milliseconds.
And the actual combustion event?
Maybe 2 to 3 milliseconds.
That is just insanely fast.
It's faster than the chemistry can keep up with sometimes. And that brings us to our second invisible force, chemical kinetics.
The speed limit.
Exactly. Equilibrium tells you what would happen if you waited forever. Kinetics tells you what actually happens in the 3 milliseconds you've got.
So thermodynamics is the destination, but kinetics is the rush hour traffic.
I like that. That's good. Reactions are a contact sport. They only happen when molecules physically collide. So first, you need a crowded room. We call that molar concentration.
The higher the density, the more collisions.
But just bumping into each other isn't enough, is it?
No. If they just gently bump, they bounce off. Nothing happens. They need to smash into each other with enough force to actually shatter their existing bonds so new ones can form.
And that minimum energy threshold is the activation energy, E.
Right, and this is all governed by the Arrhenius equation.
It is. The famous rate constant K equals A times E to the power of negative E over RT.
It looks scary, but you're right, it tells a simple story. The A part is just how often they collide.
And the exponential term is the gatekeeper. It tells you what fraction of those collisions actually have enough energy to get over that activation hurdle. And if the temperature, T, drops, that exponential term crashes towards zero incredibly fast.
And this speed limit, this is where the story gets darker, isn't it? Because this lack of time is the origin story for most of our pollutants.
It is. Let's talk about thermal nitric oxide.
Okay, so in the air all around us, nitrogen and oxygen are like strangers on a subway. They're in the same space, but they totally ignore each other.
At room temperature, yes, the activation energy to break that triple-bonded nitrogen molecule is just massive. But inside the engine, at those peak flame temperatures, 3,000 Kelvin.
We have enough energy, the Arrhenius gatekeeper opens the door.
Right, the Zeldovich mechanism kicks in. It's a chain reaction where free nitrogen atoms start attacking oxygen molecules, and suddenly you're making NO.
But wait, following our equilibrium logic, as the piston moves down, the gas expands and cools. The energy valley should shift back. The NO should want to break up and go back to being harmless N2 and O2.
It wants to. Thermodynamics says it absolutely should. But kinetics says, sorry, you're too slow.
The expansion happens too quickly.
Way too quickly. As the temperature plummets during that expansion stroke, look at the Arrhenius equation again. The rate for the reverse reaction breaking down NO just hits a wall. The rate goes to effectively zero.
So the NO gets trapped. It's frozen in the mixture.
We call it frozen equilibrium. The chemical composition is literally frozen in its high temperature state, even though the gas itself has cooled down. The NO is a fossil of the combustion peak.
And it gets pumped out the tailpipe before it ever has time to decompose. That's a really powerful image. The pollution is a snapshot of the chaos that didn't have time to clean itself up.
Exactly. And it's not just NO. Think about soot or particulates. This happens in rich zones of the chamber.
Rich meaning too much fuel, not enough air.
Right. Like in a diesel engine. Near the surface of an injected fuel droplet, it's super rich. There's not enough oxygen to go around. So the carbon atoms, they just start bonding with each other.
Forming chains and then sheets and clumps, creating those little soot particles.
And once those solid particles form, burning them back up takes even more time and heat. If the cycle ends before that can happen, you get black smoke.
And sulfur dioxide, SO2.
That one's a simpler villain. It's just an impurity in the fuel. If there's sulfur in your diesel or gasoline, it burns and becomes SO2, which leads to acid rain. The only fix there is to clean the fuel at the refinery.
And then there's the big one, carbon dioxide, the one that's unavoidable.
That one is the fundamental product. It's not a mistake of kinetics. If you burn a hydrocarbon, you're going to get CO2. The only way to stop making it is to burn less fuel or burn a fuel with no carbon, like hydrogen.
So this all comes together into what we call the engineer's dilemma.
It's a nasty optimization problem. To get maximum power and efficiency, thermodynamics demands high temperatures.
But high temperatures cause dissociation, which steals your energy. And high temperatures activate the Zeldovich mechanism, which creates smog.
You're fighting physics on two fronts. You push for efficiency, you get pollution. You lower the temperature to cut pollution, you lose efficiency, and you burn more fuel. It's a vicious cycle.
So what's the fix? How have we been cheating the system?
For the last 40 years, the main answer has been to clean up the mess afterwards. That's the catalytic converter.
The magic platinum box in the exhaust.
It's a little chemical factory.
Yeah.
It takes the unburned fuel, the CO, and the NO, and it forces them to finish the reactions that kinetics froze inside the engine.
But I've heard they're incredibly fussy.
They are. They need an almost perfectly balanced or a stoichiometric mixture of air and fuel to work. We call it lambda equals 1.
Why is that?
If you're too rich, there's no oxygen left to burn the leftover fuel in the catalyst. If you're too lean, there's too much oxygen, and you can't chemically reduce the NO back to nitrogen.
Which explains why cars have oxygen sensors and computers constantly adjusting the fuel injection. They're trying to walk that razor's edge.
Thousands of times a second. There are other strategies, like lean burn, where you run with lots of excess air.
Which lowers the peak temperature.
Right. It acts like a heat sink. Lower temp means almost no NO formation, which is great. And it's efficient. But your standard three-way catalyst stops working in that oxygen-rich exhaust. So then you have to invent whole new, complex catalyst systems. It's a never-ending game of whack-a-mole.
It feels like we're just bound by the limits of a heat engine.
We are. We're trapped by the second law of thermodynamics. As long as we're making heat to push a piston, we're stuck in this cycle of dissociation and frozen kinetics.
So is there a way to just flip the table?
Yep.
To exit this game completely?
There is. And it brings us right back to Gibbs energy, the fuel cell.
Ah, now a fuel cell isn't a heat engine at all.
Not at all. It's an electrochemical device. Doesn't burn the fuel. It takes the chemical energy, the Gibbs free energy,
Right.
converts it directly into electricity.
So it completely skips the fire step.
Which means it skips the Carnot efficiency limit.
Yeah.
And because it runs at much lower temperatures, you don't have dissociation stealing energy, and you certainly don't have the Zeldovich mechanism creating thermal NO.
So in theory, it solves both of the invisible villain problems we started with.
In theory, yes. Now, they have their own huge engineering challenges, cost, durability, hydrogen storage. But from a pure thermodynamic standpoint, they're a much more elegant way to get the energy out of a molecule.
It really changes your perspective. You think you're just pressing a pedal to go faster.
But what you're really doing is orchestrating a high-speed molecular war, trying to manage a chaotic explosion, freeze time to capture the work, and then scrub the casualties out of the exhaust.
It gives you a lot of respect for the engineers who make that happen seamlessly for hundreds of thousands of miles.
It's a miracle of control engineering that it works at all.
So to recap, the perfect burn is a myth. Real combustion is a balancing act between the energy stolen by dissociation and the ticking clock of kinetics.
And while we've gotten very good at masking those imperfections, the underlying physics hasn't changed.
Which leaves us with a final thought to mull over. We're in this massive push for zero-emission vehicles like EVs,
Right.
but we have to remember the whole system. If the electricity for that EV comes from a natural gas power plant,
You haven't eliminated the dissociation or the kinetics problems. You've just moved them from your tailpipe to a smokestack 100 miles away.
the chemistry doesn't disappear, it just relocates. The only way to truly beat the limits of the heat engine is to stop using heat engines altogether.
Whether that's solar, wind, or electrochemical cells,
Yeah.
you have to step out of the cylinder entirely. That's the only way to win the game.
A heavy thought to end on. If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.